Hey, welcome back. Today we're going to do lesson 3, which is one of my favorite lessons. We're going to be using the graphing calculator. This is on page 357. Okay, so turn to page 357. We're going to learn about regression equations and the coefficient of determination. Those are important things. But before we begin, I want to just point out this part. I'm going to show you how to use your graphing calculator. Okay, this cannot be done reasonably without regression technology, this lesson. So if you do not have a graphing calculator, please go get one now. You will need it on the mastery check as well. You cannot use your iPhone or your cell phone or whatever you got that you're using. Some of you are using the calculators in your computer, which is fine, but not for this lesson. We need a graphing calculator. So with that being said, I'm going to hop right into the warm-up number 2. 357, we want to use technology to determine the linear regression equation for each set of data. And we're just going to do number 2, and we're going to do it together starting with my fancy calculator. So essentially, this question is asking us to come up with an equation that best represents this data. So first, let's review how to, let's clear the memory. So we're going to hit second memory. All right, 7 is to reset, and then all RAM 1 and then 2. And now if we do that, I know that we are all in the same situation with a brand new calculator. The settings haven't been changed so that your keystroke should be the same as mine. All right, so the first step we have to do is put these data points into the calculator. We're going to hit the stat button and then we're going to hit enter. Okay, my keystrokes are right here. If you need them, feel free to write them down for later. We're going to put in L1, all the X values. So let's do that. And L2, let's put the Y values. Feel free to pause the video at any time if you need to pause it while you put this data in. Okay, so we're back and it looks -7.1. Give it a double check and it looks good to go. Let's look at this data in our stat plot here. We want to graph it. We want to build a little scatter plot, right? So when I hit graph, like you really don't see anything. So we have to go into stat plot. So we hit second stat plot. We need to turn the plot on. So we hit enter in the plot. We're going to turn it on and it's on scatter plot and it says the X values are in L1 and the Y values are in L2. I go back to my graph. I can kind of see those 3 points. Remember, a good way to get a good window, you can hit zoom and then 9. It'll fit those numbers in your lists. And this gives us a good little window here and we have 3 points. But remember, the question is asking us to come up with a linear regression equation. So once we have our data in there, what we're going to do, we quit and go to the home screen. Okay, let me clear this out so we know what to do once we're at the home screen. We're going to hit stat and we go over to calculate. This wants us to create a linear regression, which means a line. That's choice 4. And when you choose that, you should get this screen here. If you don't get this screen, your calculator might need to be updated. It can still do it. You just need to add some commas and your teacher can show you how to do that. All right, so this screen, what do we get? The X values are in L1, the Y is in L2, and I'm going to show you a little trick right now. If you go down to store the regression equation, we're going to hit vars for variables. We're going to tell it to store it in the Y1 variable. So we have to go over to Y variables, down to function, okay, and then we choose choice 1. Okay, when we go down now and hit calculate, we have calculated an equation which, when I hit y equals, the equation's been put into y1, so when I hit graph, it's already on our screen. So this line right here approximates these 3 points, not very well, right? I mean, these points don't look linear to me. It looks like it might be, I don't know, was that a little quadratic maybe? We'd have to check it out, but that's what today's lesson's about. All right, how do we write down our answer here? We're going to write down, I'm going to go back to the home screen. I'm going to hit enter again just so it recalculates that. And this, let's bring it over. We're going to write down, it says write the regression equation. So we have y equals ax plus b. That's a line, right? Y equals mx plus b. And we have these values here. So we're going to write that down over here. And so when you write that down, go out 3 decimal places to the nearest thousandth. That's the precision we're going to use on these for this lesson. You can just think of that as being standard. It is your turn now. You're going to do 3 all by yourself. So if you want, you can reset the calculator. Shouldn't be necessary, but go ahead and do number 3. Come up with the equation all by yourself. Go. Pause the video. Okay, so remember, if you're not getting this, go back and rewatch the steps so that you can get it into your brain how to do this and you remember those steps. For number 3, I get negative 0.829, and check this out. We're going to go out 3 places, right? So the next digit here is a 7, so this rounds up to a 9. So make sure you put a 9 there, and this 9 rounds up to a 10, so it's 610, and that's how we round those numbers. Perfect. So now you're good at linear regressions. That should be reviewed. Okay, so now let's look at page 358, because there's some words we need to learn about. We need to learn exactly what a regression equation is. Remember, the regression equation is a function that models a relationship between 2 variables in a scatter plot. So when you look at a scatter plot, you can come up with an equation that is a good approximation for all of those points. It's used to predict. Now, this term right here might be brand new to you. It's called the coefficient of determination. So what we need to do is turn this on in your calculator. It's not going to be turned on automatically. So this is one of those things you're going to have to remember. You're going to have to do it before you take your mastery check. There is no value here that's the coefficient of determination. We call it r squared. That's universally known. So I'll just call it r squared from now on. We won't use these big old words, coefficient of determination. But if you see that, it means r squared. And we have to go into the mode, hit the mode button, and then see where it says stat diagnostics. You have to go all the way down, and then we turn that on. Okay? Once we do that, let me show you what happens to the last work we did. We did this on the warm-up, right? Notice how now there's an r squared and an r. That wasn't there before. It's because we went into the mode and we turned on the stat diagnostics, and you have to do that. You only have to turn it on once and then it's on. And I don't understand why they just don't leave it on for you. But anyway, so make sure you can go into the mode, turn that on, and now we can look at these numbers right here. The coefficient of determination, this r squared, it can range from 0 to 1. And if it's 1, it means that all the points on your scatter plot are really close to your line. Let me give you an example. First, check out this formula, coefficient of determination formula. Look at this thing. This thing is ugly. This just finds r, and then you got to square it and you get r squared. But this is why you can't use your calculator. We got to use our calculator for this. So check this out. This is 2 sets of data, 2 scatter plots, and they both could be quadratic. And check this out. This one here on the left, look at how nice those points are. If we came up with an equation, most of the points would be very close to the line that we came up with, or the model. So in this situation, r would be high, and r squared would be close to 1. Okay, so maybe it's always going to be a decimal, so maybe in this case it might be like 0.95 or something very close to 1. However, on this side, see how it's a little weaker? You know, maybe we have a u here, and what do we have? Like some part of a u going up like this, and notice how the points are not so close to the line. That means r squared is not close to 1, so maybe in this case it's like 0.65. Okay, it's going to be anywhere between, r squared has to be between 0 and 1. And if it's 1, it means all the points are exactly on the line, which would never happen. That's never going to happen. But if it's a 0, it means the points are just on there randomly. There's no pattern whatsoever. And then, so the closer you are to 1, the more, the better the model is for the data. It's a better fit. Okay, that being said, let's turn to page, what do we got? 363. This data represents the absolute minimum wage in the United States over time since 1950. So we have to know how to interpret this data. You know, make sure, think about you're comfortable with this data. So when it says 5 here, that's how many years since 1950. So that'd be 1955, 1956, 1961, right? And we can go all the way down. 30 would be 1980. So that's what this data looks like. There's a whole bunch of numbers here. And here's the minimum wage. Can you believe that? Dollar by 1956, they pay you $1 an hour. Oh my goodness. But anyway, so let's put this in our calculator right now. So pause the video and put this data in your calculator. Go. Okay, so please make sure you're actually pausing the video and putting the data in. I'm in. Here's how we do it again. From the home screen, you hit stat and then enter, and then all my numbers are already in. I want to look at it, right? So you have to go to your stat plot and make sure it's turned on, and then you can hit zoom 9. Remember, we taught you that before. And we're looking at this data here. Notice I got a little piece of data right there. That's from before. That's my equation from the other problem. I'm just going to clear that out. I hit y equals. I'm going to hit clear because we don't need that anymore. That's from the other problem. But here is the equation I get. So When I look at it, obviously it's nonlinear. It's not forming a straight line. There's a curve to it. So we're going to find today better ways to represent the data. We're not going to use a linear regression like we did in the warm-up. We're going to use different types of regression. So the regressions we're going to use, we hit stat, we go over to calculate. We're going to be primarily focused with quadratic, cubic, and quartic because these are all polynomials. And so we're going to look at numbers 5, 6, and 7. So for this first one, let's look at it. Could this be the right-hand side of a quadratic equation? I don't know. Let's check it out. But first, we have to make sure that we turn on. We hit mode, and we go down, and our stat diagnostics are on. Okay, we need to make sure that's done. They should be still on from before, but if you reset your memory again, they might be turned off. So once those are on, I'm going to hit stat, calculate, and let's first do a quadratic regression. All right, so X list is in L1, the Y list is in L2, that's correct. Store the equation. All right, we're going to hit vars, go to the right, and then hit enter. We're going to store this equation in Y1 so we can look at it. Then I'm going to hit calculate. Now notice we have an R squared value here. It's 0.98. This is a quadratic regression. All right, let's look at the graph and see what it looks like. Let's zoom 9 it. And that looks pretty good. Check out that equation. It goes through the entire scatter plot pretty well. You have some points above it, some points below it. I don't see any patterns that it's not hitting. So I'm going to say this quadratic regression is pretty good because when I look at it, R squared is pretty close to 1, right? It's 0.98. That's pretty good. Here's the equation. Let's write down. We have to be careful. Check this number out right here. We see e to the negative 4. If you remember, that means it's scientific notation. That means you have to move the decimal point 4 times. 1, 2, 3, 4. So this number right here is very, very small. But let's write this information down over here, or at least we'll drag it over. So here it is over here. This is what we got out of the calculator. This would be the quadratic equation. How would we write that out as an equation? We have to know how to do that, right? We're going to go the nearest thousandth, except that first one there is kind of ugly. So let's... A lot of students, they ignore this little e, but it's really important actually because it tells you that this is 9.343 times 10 to the negative 4. So if I'm going to write that as a decimal, I need to move this 1, 2, 3, 4 times. So it's going to be 0.000934. That's what that decimal actually is. So if I were going to round it to the nearest thousandth, I'd use these squiggle lines and say it's 0.00. I'm going to draw it right here. That's got to go up to 1. So my equation would be 0.001. And this is a, and that's the x squared term, plus 0.05. Remember, we draw the line right here. That's a 7, so it's going to go up 0.052x, and then plus c, which is plus 0.462. That would be the equation that I would come up with that models this data pretty well. Ooh, I had a little dip right there. So now we can ask questions like this. You know, in the year, we'll say in the year 1960, okay? In the year 1960, predict the minimum wage, okay? So 1960, that's like 10, right? We'd have to have a 10 right here. We don't have it in our table, but we would use our line to predict it. Now, here's how you can do that in your calculator. I know we're getting so much stuff in our calculator, but as we did our regression, we put it in Y1, right? So we put the number in Y1. We have an equation in there. So one of the things we can do is from the home screen, we can go back to vars, go to the right, and we're going to hit enter and pull out a Y1. Now, 1960, if I'm looking at 1960, remember that is the number 10. I'm going to plug a 10 into my equation, and it should give me a number that predicts. If I plug that in, it says 1.07. Does that make sense? It does make sense. It's between 1 and 1.15, so that makes sense. That's how we can use our equation to predict in the future. So we could plug all these numbers in depending on what we're looking for. And that's basically creating a nonlinear model in our calculator. Now, so let's turn the page here, and then it says, let's analyze this data graphically. Same data. Use technology to determine the best regression. All right, so we just did what? We just did quadratic. Now what we're going to do is use the same data, and we're going to go through the same exact process, okay? we're going to keep our eye on that r squared, right? So, but we're going to do the whole process again. We're going to hit stat, calculate, and instead of using quadratic, now we're going to try the cubic, which you know is x to the third. We're going to put the same line in. You know what I could do here though? Vars, go to the right. Instead of putting it in y1, check this out. I can put it in y2. What is that going to do? Let's calculate. All right, so I get a new set of numbers. Let's write that over here. And after we write that down, let's create our equation. Remember, this is cubic, so we have 1, 2, 3, 4 terms on this one. So here is how I calculate, here's how I write the equation down. And you know what? Honestly, I know we're supposed to round the nearest 3 spots out, but once these decimals get really, really small, let's just write it in scientific notation. So the first number, it's negative 9.848 times 10 to the negative 6. Don't write an e because that's not standard mathematical notation. We have to write times 10 to the negative 6. And that's the x cubed number. And then the next number is the squared, and then the x, and then your regular constant number here. And let's look at our calculator once we graph that, because we put it into y2, right? So look, in y1, we have the other equation, which is the x squared. Now we have the cubic equation. When we look at the graph, we have both of them. They look very, very close. So it's hard to tell which one's better. Remember, the red one's part of a cubic, so maybe it goes up and down. You know the shape of cubics, and this is just a part of that, right? But which one fits it better? Well, the way to figure it out is to look at r squared. This is 0.9837. This is 0.984. So it just barely wins. This is barely a better model. They're both very good, but this one is just a smidge better. Here's what I want you to do. We're going to do one more here. I want you to calculate the, what are we missing here, Mr. Kelly? Calculate the quartic regression, which is x to the fourth. That's ridiculous. All right, so we'll do this one together. Quartic regression, that is 7. This time I'll put it in y3. So hit vars, go to the right, function, and then y3. That'll give me another equation that's up in there. And wow, check this out, 0.986. This looks like it's going to be our winner, right? So let's write these numbers down. And oh my goodness, look at that equation. And so some things I want to point out. Check this out. If you have scientific numbers like this, numbers in scientific notation, just write them in parentheses. That'll help keep everything straight. So notice how I put them there and there. Check what you have right here. Another thing, if you want to do plus -2, because that's negative, that's okay. Or if you just want to write minus, like we did here for the 1.36 or 1.37 when you round it, that's okay too. But look at this equation. That looks like it's the best because r squared is the strongest out of all 3 of them. So going back to my calculator, if I go to the graph, first, second, third, check that. That's a fourth. Remember, it makes like a W, but part of that W is the best representation for all this data. Did you know you can go and shut the other ones off if you want to? I'm going to shut these off. You go right on top of the equal sign, you hit enter, and then it shuts them off without deleting them, and go back. Now I can just look at my line right there, which notice the little bump in it. Because it's 4th degree, it's got a little bump in it a little bit. That's pretty cool. All right, but that's the best one. So now what we're going to do is we're going to go back to number 2, wants us to, create a graph here. So we have to make sure that we label things correctly. What are our x? Okay, x was years since 1950, right? So we're going to put time on the bottom. So the x-axis, time since 1950. Make sure we put our units. It's in years. And then on our y-axis, minimum wage, and I put a $sign. That's my unit there. And I'm going to go back and look at my list to look at my data, and I see my x values go all the way from 0 up to like 60. That would be a good one, right? So I want to end somewhere around 60. So I need to look at the x-axis and divide it out so that I end around 60. 60 needs to be about around over here so that we spread out the data. So what can we count by? Let me look at it. We'll figure it out. And the best unit I could think of was 3. 3, 6, 9, 12. All right, so we're going to count by 3s. And I didn't label every single line. I just labeled, some of the lines. So it didn't look so crowded, right? And now we're going to do the minimum wage. The minimum wage goes up to what? Like 7? Let's check that out. So we look at our numbers. It goes up to 7.25. So maybe I want to spread this out so that 8 is up here somewhere. So what do I have to count by to do that? I figured if we count by 50 cents for each line, that could be our scale, right? And we get up to 7. And I know I got to go to 7.25, but we can go up just a little bit from there. And then we put all of our points on the graph. Okay, so when I actually plot all of the points, right, you go through the points, you put them on the graph, and mine looks pretty close to what we have here on the screen. You have to approximate, right? You have to estimate, but you can do that. You're a smart kid, you can estimate these. And then we should draw that line. Uh-oh, this is where I'm going to be in trouble. And your line does not have to be exact. It just has to be, you know, close. And mine's pretty close here. You notice you have some points above and below it. And remember, you're not playing connect the dots. This is a polynomial function that goes through the points, but maybe not precisely. It's just close to them. Okay, so this is our equation, and we came up. That was the best one we came up with, right? It was the quartic. How well does the regression function model this data? Pretty well, because r squared is so close to 1. Let's write that down. All right, so let's write that down. It fits it pretty well. R squared is close to 1. And then use the equation that best models the data, predict the minimum wage in 2030. Okay, so from 1950 to 2030, that's what, 80 years? So x here would equal 80. And then x here would equal what? Well, 1950, it's years since 1950. This is 1945, so x here would equal -5 because you're going back in time. That's weird to think about, but we can do that just by plugging it in. There's two ways to do it. I showed you the other way to do it. You can just go to the home screen. We can hit, now where's my equation? My equation's in y3, right? Be careful. The equation's in y3. So I'm going to hit vars, go to the right, get my y variable. I'm going to choose y3. And now I can plug in 80 into that equation. I don't have to worry about all those decimals or anything. I get 17.008 for 80. So we can write that down. And the best part about this calculator, you can scroll up, get that number, and remember the other problem we want to use. We want to figure it out for 1945, which is -5. And that's 235. Now, some of these don't make sense in this problem. Let's do 235. So we need to have that discussion. So when we look at our polynomial function, it's very important we understand that this function that we're looking at right here, it models it great for all the points between the lowest one and the highest one on your x values. Everything in the middle here, it models it pretty well. But if you notice, this function takes a turn because it's quartic. So if we try to go outside our data set starts basically at 0, but at 5, right? Isn't that the first number we have? First number we have is 5. So if we go outside of that, like that -5, then our model will not be reliable. $2.35, how's that going to be possible back in 1945? That's not possible. So make sure you understand that within the data points, it's okay. Outside the data points, not reliable. Okay, so now complete on the next page here. What page is this here? We got 365. Complete 4a and 4b using the same equation. Go ahead and complete 4a and 4b. Okay, so here's what I get. For 1865, that would be -85, right? That's not anywhere near our data set. So it tells us it's $362. So that doesn't work, right? So do you think a cubic model, which remember we had a quartic, but do you think a cubic model is appropriate? No, a model can predict within the data set, but not far outside of the data set. Okay, let's look at one more type. I know this is a long video. Let's look at one more type of problem. This is going to be on your own. Let's go page 366. So now it's time for you to try this by yourself. You're going to pause the video, and then I want you to do this whole problem, which means you have to find 3 regressions, find the best one. This data represents the average monthly precipitation in Pittsburgh, Pennsylvania. So go ahead and answer number 1 and 2. Find your 3 regressions by yourself. Ready, set, go. Okay, so here's what I got. I did it 3 times, and look, once again, it's the quartic regression here that has the best r squared. You have to look at r squared, and look, it just gets better and better, because look at this data. It finds that maximum point right there, and it seems to model the data pretty well. So let's write that equation out. All right, we'll write it down here, and interpret the coefficient of determination. That is the r squared. So here's what I have for the equation. Remember, I'm just copying it off of the output from the calculator, and then interpret the coefficient of determination. Remember, that is r squared. So r squared equals 0.80. That's what it tells me right here. And we can put a 1 there if you want to. The model is a pretty good fit because r is close to 1. It's pretty close to 1. Could be closer like in our other example, but it's not too bad. So remember, that's r squared, not just r. is pretty close to 1. Now it says use your equation to make predictions. You know, we can predict in the middle part it's going to be higher, and then on the ends here it's going to be lower. And remember, this correlates with the month. So we could say the middle of the months, which is summer, it rains more. That's what basically, right? So the precipitation is higher in the middle part or in the summer. So we can write that out. So we can just make a statement that says, it appears as though we can expect more precipitation during the summer months. That is basically summarizing it. And that's it. I know this was a long video, but there's a lot of stuff we have to do. If you need help, please ask your teacher. This is Mr. Kelly and K-Town. Remember, it's nice to be important. It's more important to be nice. See you.